All right, let's take a look at the slides, the lecture slides for chapter 3, the normal distributions. In chapter 3, we cover density curves, describing density curves, normal distributions, the 68, 95, 99.7 rule, the standard normal distribution, finding normal proportions, and using the standard normal table, finding a value given a proportion. Density curves. We now have a toolbox of graphical and numerical methods for describing distributions. What is more, we have a clear strategy for exploring on a single quantitative variable. Exploring a distribution. Always plot your data. Make a graph, usually a histogram or a stem plot. Look for the overall pattern, shape, center, and variability, and for striking deviations such as outliers. Calculate a numerical summary to briefly describe center and variability. Now we add one more step to this strategy. Sometimes the overall pattern of a large number of observations is so regular that we can describe it by a smooth curve. Example, here is a histogram of vocabulary scores of 947 seventh graders. The smooth curve drawn over the histogram is a mathematical model for the distribution. The areas of the shaded bars in the histogram represent the proportion of scores in the observed data that are less than or equal to 6.0. This proportion is equal to 0.303. The shaded bars represent scores less than 6.0, less than or equal to. And you see the darker shaded bars represent about 30% of the bar area itself. Now the area under the smooth curve to the left of 6.0 is shaded. If the scale is adjusted so that the total area under the curve is exactly 1, then this curve is called a density curve. The proportion of the area to the left of 6.0 is now equal to 0.293 because we have a little bit of the bars going outside and we've lost some preciseness there by smoothing out our bars. A density curve is a curve that is always on or above the horizontal axis, has an area of exactly 1 underneath it. A density curve describes the overall pattern of a distribution. The area under the curve and above any range of values on the horizontal axis is the proportion of all observations that fall in that range. Caution, no set of real data is exactly described by a density curve. Median and mean of a density curve. The median of a density curve is the equal areas point, the point that divides the area under the curve in half. The mean of a density curve is the balance point, at which the curve would balance if made of solid material. The median and the mean are the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve is pulled away from the median in the direction of the long tail. The mean and standard deviation computed from actual observations data are denoted by X and S respectively. Maybe X bar and S, right? The mean X bar and S. The mean and standard deviation of the actual distribution represented by the density curve are denoted by mu and sigma respectively. One particularly important class of density curves are the normal curves, which describe normal distributions. All normal curves are symmetric, single-peaked, and bell-shaped. Any specific normal curve is described by giving its mean mu and standard deviation sigma. Unlike most distributions, any particular normal distribution is completely specified by two numbers, its mean, mu, and its standard deviation, sigma. The mean is located at the center of the symmetric curve and is the same as the median. Changing mu without changing sigma moves the normal curve along the horizontal axis without changing its variability. The standard deviation sigma controls the variability of a normal curve. When the standard deviation is larger, the area under the normal curve is less concentrated about the mean. The standard deviation is the distance from the center to the change of curvature points on either side. Normal distributions. A normal distribution is described by a normal density curve. Any particular normal distribution is completely specified by two numbers, its mean mu and standard deviation sigma. The mean of a normal distribution is at the center of the symmetric normal curve. The standard deviation is the distance from the center to the change of curvature points on either side. The 68-95-99.7 rule. The normal distribution with mean mu and standard deviation sigma has approximately 68% of the observations fall within sigma of mu. Approximately 95% of the observations fall within 2 sigma of mu. And approximately 99.7% of the observations fall within 3 sigma of mu. So 1 standard deviation away from the mean, above and below, gets us 68% of the observations. 2 standard deviations away from the mean, above and below, covers 95% of observations. And between 3 standard deviations below the mean and 3 standard deviations above the mean, our distribution covers 99.7% of the observations. The distribution of Iowa test of basic skills vocabulary scores for 7th grade students in Gary, Indiana is close to normal. Suppose the distribution is N with mean 6.84 and standard deviation 1.55. Sketch the normal density curve for this distribution. So we start by drawing a normal curve where at 1 standard deviation below and 1 standard deviation above, that's where we've hit this curvature change from going concave up to concave down to concave up. And then also each tick mark away from the mean is equidistant, and the distance is the length of a standard deviation. What percent of ITBS vocabulary scores is between 3.74 and 9.94? That's 2 standard deviations below and 2 standard deviations above. So about 95% of the scores are within 2 standard deviations of the mean. What percent of the scores is above 5.29. Oh, let's go back to our picture. I think that's this one. Let's see, above 5.29. If we take and draw a line at 5.29, then they're asking us for what area is represented by this amount, right? So that is 1 standard deviation below plus 50%. So let me grab, so at this point, we have 0.5, right? We have 50% of the data falling to the right of the mean. And between the mean and 1 standard deviation below, we're looking at half of that 68, right? So we have 34 here. So 0.34 plus 0.5 means that we have 84% of the observations score is above 5.29. So 84%. All normal distributions are the same if we measure the units of size sigma from the mean mu as center. Changing to these units is called standardizing. Standardizing and z-scores. If x is an observation from a distribution that has mean mu and standard deviation sigma, the standardized value of x is x minus mu divided by sigma. So that's the z-score, the standardized value. A standardized value is often called a z-score. The height, here's an example, the height of women aged 20 to 29 in the United States are approximately normal, with mu equal to 64.2 and sigma equal to 2.8 inches. The standardized height is height minus mu divided by sigma. A woman's standardized height is the number of standard deviations by which her height differs from the mean height of all women aged 20 to 29. A woman 70 inches tall, for example, has a standardized height of 70 minus 64.2, that quantity divided by 2.8, which yields 2.07. So she has a z-score of 2.07 or 2.07 standard deviations above the mean. Similarly, a woman 5 feet or 60 inches tall has a standardized height of 60 minus 64.2, that quantity divided by 2.8, which yields negative 1.5, which tells us that she has a z-score 1.5 standard deviations below the mean. So 1.5 standard deviations less than the mean height. The standard normal distribution is the normal distribution with mean 0 and standard deviation 1. If a variable has any normal distribution written in parentheses mu comma sigma with mean equal to mu and standard deviation equal to sigma, then the standardized variable z equals the difference between the observation and the mean minus, divided by the standard deviation. And that takes on the form of 0 for center and a standard deviation of 1. So we have mu equal to 0, standard deviation equal to 1. This is a normalized, this is standardized. So the normal curve is the one peak bell-shaped distribution. The standardized normal curve then has this equation attached to it where we're looking at z-scores. Cumulative proportions. A cumulative proportion for the value x in a distribution is the proportion of observations in the distribution that are less than or equal to x. So we're going from the left to the right and we're collecting percent of the distribution as we go along. Example, who qualifies for college sports? The combined score of the almost 1.7 million high school seniors taking the SAT in 2013 were approximately normal, with mean 1,011 and standard deviation 216. What percent of high school seniors met this SAT requirement of a combined score of 820 or better? Here is the calculation in a picture. So we're looking for the area to the right of 820. The total area equals 1. The total area under the curve equals 1. So to find the value less than they did this opposite on me. So let me regather. So we want the scores greater than 820. So that's the first image. But what they're telling us is if we know the area is 1 under the whole curve, and we take out the cumulated percentage that is left of 820, which in their chart they've looked up to be 0.187, then what we have is a resulting area of the first image we saw, which then through these values we see is a proportion of 0.8127. So about 81% qualified for college sports. Normal calculations using software. So to find the numerical value of 0.1873 of the cumulative proportion in our college sports example using software, plug the mean and standard deviation of 1,010 and standard deviation of 214 and ask for the cumulative proportion for 820. Software often uses terms such as cumulative distribution or cumulative probability. Minitab's output looks like this, where they've restated our input and given us the output of 0.1873, which matches. The standard normal table. Because all normal distributions are the same when we standardize, we can find areas under any normal curve from a single tab, from a single table. The standard normal table. Table A is a table of areas under the standard normal curve. The table entry for each value z is the area under the curve to the left of z. Suppose we want to find the proportion of observations from the standard normal distribution that are less than 0.81. We can use table A. So we go to find the z-score. Let me get my annotator out. Oh, they did it for me, so I don't have to. Okay, so on the z, you're looking at the tens place in a column and the hundreds place in the row. And once you find the intersection of the 0.8 and the 0.01, which represents your z-score of 0.81, then the overlapping area, the overlapping space in the box, 0.7910, is the area under the curve to the left of the entry, the observation, because we're looking at accumulation, right? Cumulative proportions. Normal calculations. Find the proportion of observations from the standard normal distribution that are between negative 1.25 and 0.81. So area to the left of z equals 0.81 was 0.7910, and area to the left of the z-score negative 1.25 is 0.1056. If we subtract the area to the left from the image that we have on the right, then we'll get the final image, right? So we're like punching out that corner over there to get just what's left in the middle. And then we're between negative 125 and 81, right? Which is what we want. So we have the result of having to subtract the areas to get 0.685. So the area under the curve between those two z-scores is 0.6854. Can you find the same proportion using a different approach? They're saying you could find the area to the left of 125, negative 125, and to the right of 0.81, and just subtract those individually, or add the two white areas together and take it away from the whole, leaving you with the red area, which is 0.854. So one thing I love about math is that there are multiple approaches to the correct answer. Using table A to find the normal proportions. Step 1, state the problem in terms of the observed variable x. Draw a picture that shows the proportion you want in terms of cumulative proportions. Step 2, standardize x. To restate the problem in terms of the standard normal variable z. Use table A and the fact that the total area under the curve is 1 to find the required area under the standard normal curve. Find the value given a proportion. So that would be working the problem in reverse. SAT reading scores for a recent year are distributed according to a normal distribution where the mean is 504, and the standard deviation is 111. How high must a student score in order to be in the top 10% of the distribution? We'll look at the same two approaches we did for finding normal proportions, but using software and then using table A. finding a value given a proportion. Example using software. So using the software, we want to find the SAT score X with the area 0.1 to its right under the curve, normal curve with mean mu equals 504 and standard deviation sigma equal to 111. That's the same as finding the SAT score X with the area 0.9 to its left. Most software will tell you X when you plug in the mean 504, standard deviation 111, and cumulative proportion 0.9. Here's the mini tab output. So they're inputting the mean and the standard deviation as well as inputting the proportion, and they're getting back the X value. In calculations, we have the SAT reading scores for a recent year are distributed to a normal distribution with mean 504 and standard deviation 111. How high must the student score be in order? How high must the student score in order to be in the top 10% of the distribution? In order to use table A, equivalently, what score has cumulative proportion 0.90 below it? So we've drawn ourselves a standard normal curve and we've shaded the area that we're looking for. And so that's what we're asking ourselves right now. Look up the closest probability, closest to 0.10 in the table, and find the corresponding standardized score. The value you seek is that many standard deviations from the mean. So this is going to give us a z-score, right? So the one that's closest to a 10% is a 0.8997. That's the highest percentage we get, closest one we get. Oh, they're going for 90, not 10. So here they've gone, because in this table, we're looking for 90%, like we typed into the calculator on the last slide. So the closest value to 0.90 is 0.8997. That's going to give us this z-score of 1.28. This 1.28 is saying that to the left of 1.28, we have about 90% of the information. So 128 gives us the z-score 1.28. And now we need to unstandardize this z-score from the observed value. So we start with our z equals the quantity x minus mu divided by sigma. Okay, so we need to unstandardize the z-score to find the observed value x. And we do that by taking x minus mu and dividing that quantity by sigma to find the z-score. That's how we standardize. So we're going to take the z-score that we're given, that we found, 1.28, and we'll plug it in for z. And we were given mu, we were given sigma. So one thing that they do is they first solve for x, and then they plug in the values. You're welcome to plug in the values and then solve for x, but this method is a little more straightforward. So we take the mean plus 1.28 times 111 to find the value 646.08. So what we're saying is that how high must a student score in order to be in the top 10% of the distribution? They must score 646.08 or higher to be in the top 10% of the distribution of the SAT reading scores for this particular year. Backward normal calculations. Using table A, give a normal proportion. Step 1, we state the problem in terms of the given proportion. We draw a picture that shows the normal value x you want in relation to the cumulative proportion. Step 2, use table A. The fact that the total area under the curve is 1 and the given area under the standard normal curve to find the corresponding z value. And step 3, unstandardize. So unstandardize z to solve the problem in terms of a non-standard normal variable x.